As manufacturing evolves with increasingly stringent precision requirements, CMMs have become indispensable for quality assurance across industries, particularly in aerospace where micron-level tolerances are critical for performance and safety. What is a CMM? CMMs acts as a 3D ruler, using a probe to measure part dimensions and compare them against CAD models for accuracy, are one of the most important devices for GD&T geometry dimensional and tolerance inspection. It is widely used in industries like automotive manufacturing, aerospace, and high-end equipment manufacturing. CMMs have become an essential tool for products quality control. Based on structural and functional characteristics, CMMs can be categorized into several types. Bridge-Type CMM. As the most classic type, the Bridge-Type CMM features a movable horizontal arm and fixed vertical columns, offering excellent rigidity and stability. Its high precision makes it the preferred choice for GD&T inspection, especially in industries like automotive and aerospace where tight dimensional tolerances are required. However, it occupies a large footprint and typically requires fixed installation, lacking portability. Cantilever-Type CMM. This type uses a single-sided supported horizontal arm, with a compact design that maximizes space utilization, making it suitable for environments with limited space, such as workshops or laboratories. Its open design allows for easy loading and unloading of components, often used for rapid inspection of small to medium-sized parts like sheet metal or plastic components. However, due to relatively lower rigidity, it is suitable for medium precision applications. While it occupies less space than Bridge-Type CMMs, it still requires fixed installation and is not easily movable. Gantry-Type CMM. Designed for oversized parts, this type features an overhead gantry frame and dual high-precision guide rails, with a measurement range that can extend tens of meters. It requires a fixed foundation for installation, offering exceptional stability. It is ideal for GD&T inspection of heavy or extra-long components like aircraft fuselages, ship parts, and wind turbine blades. However, it occupies the largest footprint and typically requires specialized foundations and factory space, making it immobile. Horizontal arm CMM. With its horizontally extended measuring arm, this type is particularly suited for flat or thin-walled workpieces, such as automotive bodies or sheet metal parts. Compared to Cantilever-Type CMMs, its bridge can move vertically along a single arm, balancing openness and stability. It excels in three-dimensional inspection of large components. While it occupies slightly less space than Bridge-Type CMMs, it still requires fixed installation and is not easily movable. Articulated arm CMM. This type uses a multi-axis rotating arm to achieve flexible measurement, offering high portability. It can be easily moved to the workpiece for on-site inspection. Its high degree of freedom makes it suitable for measuring complex surfaces or hard-to-reach areas, often used in mold debugging or rapid sampling on production lines. However, it is sensitive to environmental vibrations, and its precision is slightly lower than fixed CMMs. Its compact size allows it to be handheld or moved to different locations, making it the only truly portable CMM. Limitations of CMMs. Measurement efficiency. Designed for precision, their measurement speed is relatively slow, making it difficult to meet rapid inspection demands in large-scale production. Measurement range. The measurable range is limited by the machine's structure, and oversized or heavy components may exceed the capacity of some models. Probe compatibility. Contact-type probes can only measure surfaces they physically touch. Probe tip size must correspond to the measured features. Oversized tips may result in missed measurements of complex part details and internal features. Material suitability. When measuring soft materials like rubber or elastomers, contact measurement can cause deformation, leading to data inaccuracies. How does a CMM work? Import CAD model. Load the part's 3D CAD model into the measurement software and establish a reference coordinate system. Ensure the model matches the actual part version to avoid errors due to design changes. Extract measurement elements. Identify key measurement features, e.g. hole positions, planes, contours, from the CAD model, defining theoretical dimensions and tolerances. Plan probe point distribution to cover all critical quality control points. Set evaluation criteria based on 2D drawings. Refer to engineering drawings to define dimensional and geometric tolerances in the software. Select probe and configure angle. Select the appropriate probe based on the geometric features being measured. Adjust the probe head angle to ensure full access to all measurement areas while avoiding collisions. Fixture workpieces and alignment. Secure the part using dedicated fixtures or the CMM work table to ensure stable, distortion-free clamping. Perform rough alignment manually or automatically to preliminarily match the part with the measurement coordinate system. Set operation parameters. Adjust measurement speed, optimize scanning path, set safety planes to prevent probe collisions. Run measurement program. Initiate automatic measurement mode where the device collects data following the predefined path. Generate inspection report. After measurement, the software automatically compares actual measurements with CAD nominal values, calculates deviations, and exports visual reports, PDF/Excel formats. Conclusion. Zintilon, we are equipped with advanced size CMMs and CNC machines, including Hermel, Makino, and Fanuc, to ensure every part meets strict quality standards. Visit our website to learn more about our quality commitment. Need precision parts? Upload your drawings now for a quote.